Okay, so I'm going to talk more about Chapter 2 today. So I'm going to define distance again, which I have already done it, but if you notice, the what I'm actually writing is slightly different. It's still the same definition, but what I wrote is a bit different. So I believe I originally defined the distance in a graph G between two vertices u and v. It was the length of the shortest uv path in G. Now I'm saying it's the length of the shortest uv walk in G. Why is that the same? Just take a look at this note down here. If you recall Theorem 2.1 in the book, that was the theorem that we proved. It says that the shortest walk between any two vertices is always a path. So the shortest UV walk is going to be a path anyway. So if I write walk here, there's no danger that the shortest UV walk isn't going to be a path. So this is the same definition. And by the way, such a walk, in other words, a walk that has minimum length, is called a UV geodesic. So here's some facts about distance that are not proven in the book, and I'm not going to write formal proofs for all of them. Actually, I'm going to talk about each one and why it's true. Some of these are fairly easy to see why they're true if you just think about the definition of distance. So let's go through the easy ones. These facts, by the way, are at the top of page 45 in the book. So for all vertices u and v, the distance from u to v is greater than or equal to 0. Yeah, that's just because the distance between two vertices is the length of a walk. It's the shortest length of any walk from u to v. The length of a walk is always a non-negative integer. So whatever this number is, it's the length of a walk, and so it has to be a non-negative integer. It has to be greater than or equal to 0. All right, next one. For all vertices u and v, the distance from u to v is 0 if and only if u equals v. So basically, this just follows from, we have an if and only if here, so why don't we just examine both directions? Probably the direction from here to here is easy to see. If u and v are the same vertex, then the distance from u to v would be 0. A walk, you can have a walk that starts and ends at the same vertex, and right, like, yeah, maybe if I can just make a bubble. You can have trivial walks, like a walk. Normally, I denote a walk by just listing a sequence of vertices. That sequence can just consist of one vertex. This walk starts at v and then immediately ends at v. We would say that this walk has length 0 because the length of a walk is always 1 less than the number of vertices in the sequence. So this sequence has 1 vertex, so it has length 0. So this is basically like, because we have these trivial walks, this is why the distance from a vertex to itself is 0, because you can start at that vertex and then end at that vertex, and that's a walk of length 0, and you're not going to get a shorter walk than that, so that's the shortest one. So that's why this implies this. But also, this implies this because if I didn't have the same vertex, if I had two different vertices, then I can't get from u to v with a walk of length 0. The only walks of length 0 are precisely the trivial walks, and they always start and end at the same vertex. If you want to end at a different vertex from what you started at, you can't have a walk of length 0. So that's why this implies this. Let's talk about property 3. For all vertices u and v, the distance from u to v equals the distance from v to u. And this is, when you talk about these things in math, so sometimes it's easy to just sort of say, you know, of course the distance from u to v is equal to the distance from v to u, because we're using the word distance, and the word distance sort of brings to mind all of these intuitive ideas of how we think of distance in the physical real world. But in math, this can be misleading. In math, we sometimes use words that mean things in math that don't necessarily follow our intuition about the real world. So let's think about what this actually means. This means the shortest walk that starts at u and ends at v, and this means the shortest walk that starts at v and ends at u. And why would those be the same thing? It's basically because you can always just reverse the direction of a walk. Because a walk would be a sequence of vertices. The first one here would be u, the last one here would be v, and like you have to, like, the consecutive vertices in the walk are all neighbors of each other. I can just write that same sequence backwards, and then when I write it backwards, it will start with v and end at u, and when I write it backwards, it's going to have the same length. So if you give me any walk from u to v of any particular length, I can just write that walk backwards, and that'll give me a walk from v to u of the same length. So whatever the shortest length is from u to v, that would be the same as the shortest length from v to u. So that's why this is true. It's because you can always just write the sequence of vertices in a walk, you can write it backwards. So let's talk about number 4. By the way, number 4 is called the Triangle Inequality. This is a common thing in math, and this is an important property that we really ought to have for something that follows any kind of intuitive notion of distance. Let me explain. Basically, what this says is, if you want to get from u to w, that one way you can do that is you can go from u to v and then go from v to w. That may not be the fastest way to get from u to w, but that is a way. So this number here represents intuitively the shortest way to get from u to w. And this over here represents the shortest way to get from u to v, and then the shortest way to get from v to w. So it's like, if you, this here is like the shortest way to get from u to w if you have to go through v somehow. And this here on the left is just the shortest way to get from u to w, whether you go through v or not. But, oh, right, one more thing. It kind of invokes a picture. This is a pretty abstract picture that I'm drawing. This isn't like a real particular graph. This is just sort of like an intuitive cartoon of how we think of these things. Here's the distance from u to w, and if I want to go through v first, I would go distance from u to v. Plus the distance from v to w. So basically, this picture is just kind of why we call this the triangle inequality, just because we have three vertices and we're talking about these distances. And by the way, in geometry, if like this was a geometric triangle and these distances were line segments, it would be true that this distance is less than or equal to this distance plus this distance. Anyway, let's actually get back to more technical math here instead of the intuition and prove this. So let's say P1. I want P1 to be basically this geodesic. So there's from U to V, there's some shortest UV path. So there's some path that starts at U. So the vertices in my path are going to be x sub 0 through x sub L1. And x0 is going to be the same as U, and the last vertex here is going to be the same as V, so this is a UV path. And in particular, I'm going to let it be a UV geodesic, so this is a shortest UV path. So in particular, I wrote the length of this path is L1. L1, since this is a geodesic, this is one of the shortest UV paths. So L1 is the same as the distance from U to V. That's what the distance from U to V is. It's the length of a shortest UV path. And similarly, let's get a VW geodesic. So P2, I'm going to write something similar. Oh, I can't use x's. So let's say y sub 0 should be v, and then y1, y2, all the way up to y sub whatever the length of that path is. And the last vertex should be w, because we're doing a VW geodesic. And so L2, the length of that path, is the distance from V to W. And remember what I said when I was sort of discussing the intuition behind this, because the intuition is really going to guide part of the proof here. What I said was the shortest way to get from U to W is at most the shortest way to get from U to V and then from V to W. So what we have with P1 and P2 is I have a way to get from U to V, and then I have a way to get from V to W. And that gives me a way to get from U to W. So consider the following walk. And these other ones were paths because these were geodesics. But I'm not going to claim that what follows is a path, but it is going to be a walk. And it's just going to consist of basically this sequence of vertices followed by this sequence of vertices. So x naught, which is the same as u, and then I'm going to go x1 all the way up to x sub L1, which is the same as v, which, by the way, is also the same as y naught. From here, I'm going to pick up with the y's. So y1, y2, all the way up to y sub L2, which is w. So here I have a walk. It started at U, it ended at W, and by the way, it is indeed a walk. The only requirement for a walk is that consecutive vertices have to be adjacent. So x0 has to be adjacent to x1, x1 has to be adjacent to x2, but they are because this sequence of vertices came from up here, and this was a path, and because this is a path, we know consecutive vertices are adjacent up here. So yeah, maybe a better way to say it is, since consecutive vertices are adjacent up here and also down here, that when I take this sequence and then I just stick this sequence on the end of that sequence, it's still true. Consecutive vertices are still adjacent. So here we have a a walk. W is a UV walk of length. Well, what is the length? The easy way to get the length is to just just add the two lengths of the things that we put together to get this. So it would be L1 plus L2, which is the distance from U to V, plus the distance from V to W. So look what we did. We have a walk from U to W of length this. Now, what I really want, once again, what I really want is to prove this. But we're basically done here. The distance from U to V. This here is the length of the, okay, I shouldn't say the shortest walk because there can be a tie for shortest walk. It's a bit dangerous to say the shortest walk, so I should say a shortest walk, or the smallest, the minimum length of a walk. So let me start over here. The distance from U to V is the length of a shortest walk from U to V. Up here I have a walk from U to, let me start over again. So what I really want is U to W. The distance from U to W is the length of a shortest walk. This should have been a W as well, from U to W. What we have up here is a walk from U to W that may or may not be the shortest. But whatever the shortest is, since we already know that there's a walk of this length, the shortest length is less than or equal to this. And that's all we wanted to know. I just took too long to explain that last part. So that's the proof of 4. Okay, so then let me talk a bit about eccentricity. So say we have a graph G and a vertex V. We say E of V, which we call the eccentricity of V. It's the distance to the farthest vertex, farthest away from V. In other words, it's the maximum distance from U to V where you take the maximum over all vertices U. So it's like you find the farthest away vertex U, and the eccentricity of V is the distance to that farthest vertex U. Also, we define the diameter of a graph to be the maximum eccentricity and the radius to be the minimum eccentricity. And this is another spot in math where suddenly we're using words that, these are sort of like loaded words, radius and diameter, because we all know the radius of a circle and a diameter of a circle. And geometry is, geometry is math, but it's quite different from graph theory. maybe in abstract ways they're not that different, but in sort of more concrete ways they are different. The diameter and radius of a graph don't have that much to do with the diameter and radius of a circle unless you want to be abstract about it. So it can be dangerous to make assumptions. We have a theorem 2.8. I'm not there's a proof in the book, and the proof is not that long, so I'm not going to go over the proof. But what it says is that for all graphs G, the radius is less than or equal to the diameter, which is less than or equal to 2 times the radius. So what I'd like to do is just talk about why this, why can our intuition fail to be true? Like, intuition that just comes from the fact that diameter and radius are just loaded words. So in particular, if you just come in with your preconceived notions of diameter and radius, you might say the diameter is always going to be equal to 2 times the radius, because that's true of circles. But it's not. So why not? It's easy to come up with examples where it is. Like, I don't know, how about this graph? So actually, this is like a good exercise to help understand eccentricity and diameter and radius. I can just go here, and I'm going to label each vertex with its eccentricity. So a lot of times when I write a symbol next to a vertex, that's the name of that vertex. That's not what I'm doing right now. So these labels are not going to be the names of the vertices. It's just going to be the eccentricity of the vertex. So once again, eccentricity is the distance to the farthest vertex in the graph. So the eccentricity of this vertex, let's see, this vertex is distance 1 from that vertex. This vertex is distance 2 from that vertex. So the farthest distance from this vertex is a distance of 2. So the eccentricity of this is 2. Similarly, the eccentricity of this vertex is going to be 2. It's kind of the mirror image of that vertex. What's the eccentricity of this vertex? Well, it's the distance to the farthest vertex, and this is a pretty small graph, so I can really just check all the distances. So this vertex would be a distance 1 from here. This vertex would also be a distance 1 from here. So this is a 1. And the diameter of a graph is the largest eccentricity. So the largest number I see here is 2. The radius is the smallest eccentricity. So the radius is going to be 1. Why don't I draw another graph? Yeah. How about this graph? So, yeah, let me do the same thing here. I'm going to label each vertex with its eccentricity. Now, there's these far out vertices around the outsides. So let me pick one. I'm going to say I claim that the eccentricity here is 4. And maybe there's more to check here, and I'll go kind of fast, but what's the farthest vertex from this? I can find all the distances. This would be distance 1 away, this would be distance 2, this would be distance 2, this vertex would be distance 3, right, because I've got to go 1, 2, 3 to get to that vertex. But the farthest distance from here is the distance from this to like maybe this one. So the distance from this one to this one would be 4. 1, 2, 3, 4. The distance from this one to this one would also be 4. 1, 2, 3, 4. The distance from this one to this one would also be 4, and the distance from this one to this one would also be 4. And if you check all the distances, you're not going to find anything farther away than 4. So the eccentricity of this vertex is 4. In fact, the eccentricity of all of these, what I called them, these outer vertices, is going to be 4. The eccentricity of these is all going to be 3, and I'm going fast here. I encourage you to think about why this is, why I'm putting these 3s there. The eccentricity of this middle vertex is going to be a 2, and it's maybe that one's easier to see. You can check that this one, for example, this has a distance of 2 to any of these outer vertices. 1, 2, 1, 2, 1, 2. 1, 2. And you're not going to find anything that's farther away than a distance of 2 from this vertex. So after putting these labels down, the diameter is just the largest one, so the diameter is 4. And the radius is the smallest one, so the radius is 2. So I just kind of wanted to draw these examples, and in a way I'm kind of just misleading you even more, because I just decided to draw a few examples where the diameter is exactly equal to twice the radius. So that was true in this one and in this one. And so now I'm going to draw some examples where that's not true. How can the diameter not be equal to twice the radius? Well, there's one really easy way. The diameter can just be an odd number. If the diameter is an odd number, because keep in mind that we're in a world where everything's an integer. In graph theory, at least for everything that we've defined so far, like everything's an integer. The length of walks in a graph is always an integer. So if the diameter is an odd number, it can't be twice the radius, because that would always be even. So yeah, how about this graph? I was going to draw more, but I don't have to. This is a graph of diameter 1. How do I know? This vertex has eccentricity 1. This vertex also has eccentricity 1, because the farthest vertex is a distance of 1 away from here, and the farthest vertex is a distance of 1 away from here. So the diameter is the largest of these eccentricities, which is 1. The radius is also 1. What I was going to draw before I realized I could just stop, I was going to draw this graph. It's basically a path of length 3. So this vertex has eccentricity 3 because the farthest away is a distance of 3. This one would have eccentricity 2, 2, and then this one would be 3. So the diameter here would be 3. The radius would be 2. Of course, the inequality is still true in the theorem. The diameter is less than or equal to 2 times the radius. 3 is less than or equal to 2 times 2. But it's not equal. So that's one way. The diameter can just be an odd number. But then let me draw at least one more example. Why don't I just draw, let's see. A cycle of length, say 8. The length isn't that important. I just chose 8. Let's talk about the eccentricities of vertices on a cycle. Like the eccentricity of this vertex. So I find the farthest distance. So this would have a distance 1. This would also have a distance of 1. This would have a distance of 2. And of course, this would also have a distance of 2. This would have a distance of 3. Same here. The one directly across from it would have a distance of 4. And so this has eccentricity 4. Right? What's the eccentricity of this vertex? Well, basically by symmetry, they're all going to have the same eccentricity. Because when I ask, what's the eccentricity of this vertex, I'm trying to find the farthest vertex from here. The farthest one is going to be the one like directly across from it on the cycle, and the distance is going to be 1, 2, 3, 4. Either way you go. So this has an eccentricity of 4. They actually all have an eccentricity of 4. So here, it's not the same thing from last time. The diameter isn't an odd number, because remember, I said last time, if we can just make the diameter an odd number, then of course it's not going to be equal to 2 times the radius. But this time that didn't happen. The diameter was an even number. And still the diameter is not equal to twice the radius. In fact, the diameter and radius are the same. Okay. And right, in general, in a cycle, the diameter and the radius are always going to be the same. If it's a cycle of even length, then the diameter and radius are both just going to be half the length. Like this is a cycle of length 8, the diameter and radius are both half of that. If it's a cycle of odd length, then maybe I can let you figure out what the diameter and radius are. But the diameter and radius are going to be the same thing, even if it's a cycle of odd length. Okay. Maybe, yeah, I should probably make a new video, so I'm going to cut this off.